Well, welcome back, statistics scholars. I'm once again Dr. Jennifer Moses, your instructor for this course. And you should have open the slides entitled Data, because this lecture is all about sort of the basic conceptual framework, vocab words, and ideas that are going to become our working vocabulary for this semester. And the slides are entitled Data on Canvas, and so make sure you have those slides available to you so you can take notes on them. Because remember, the research is really clear that if you actually physically take notes with your hands, actually physically write, you'll do much better in the course. So make sure to have those notes available, have those notes out, and be writing. So to begin, what is data analysis? I think that's the most important place to start, right? Because this isn't a math class, right? I said that from the very get-go. It's more like an engineering class or a physics class that uses math as a tool, rather than being a math class itself. It's not that we're not going to do math in here, we will, but it's only about 30–40% of the class, and the rest of the class is learning about the concepts behind the science of data analysis. And so we have to sort of start learning those concepts right away, long before we learn to calculate anything. It's a concept class, not a math class, although math is a tool. So what is the purpose of data analysis? Well, the purpose of data analysis is to gather information from people. Gather information from people. And that information that we gather from people is called data. Right? And I say people because this is a social science class. It's a psychology class. Well, I'm a psychologist anyway, teaching it. But the whole idea is to learn the statistics that we use when we talk about people, right? Exactly. So data analysis is about gathering information from people in order to ask and answer research questions. Now, what is a research question? Well, a research question is sort of like this. Do men and women differ in terms of aggression? That is an example of a research question that a social scientist might ask. It's an interesting question. And in order to answer that question, we're going to have to gather information about aggression from both men and from women. So I guess we're not interested in people who are intersexed or who don't feel like they fit cleanly into either of those categories, but I digress. That is an example of a research question. Do men and women differ in terms of aggression? So it's an interesting research question. And when you gather information from men and women about their aggression, you're going to gather information about their gender, data, and you're going to gather information about their aggression, data. Or how about, is mental health more of an urban or a rural problem? That is also a research question that data analysis can help us answer. Or how does age impact cognitive functioning? Another research question. And when both of these questions, you're going to have to gather information from people, gather data from people that you're going to have to analyze. And then statistics becomes the mathematical tool to make sense of that data, to figure out the answers to those questions. So, what is data then? Well, as I mentioned, it's information. It's information that you gather from people about some phenomenon, some characteristic that you care about. And we call that characteristic a variable because we're only going to gather information from people on characteristics on which we think they can vary. So that word variable is another vocab term. This idea that people can be different. Hair color is a variable. Now, being blonde isn't a variable. That's my outcome. That's my data. Being blonde is my data. I might tell someone over the phone, let's say I'm making an appointment for, I'm going to get my hair dyed. And they say, well, what color is your hair? And I'm going to say my hair is blonde, or my hair is, dirty blonde, or something like that, light brown. And that my answer to the question is my data. And the variable, though, that I gave my answer to is hair color. Hair color is sort of the broad characteristic on which people can differ. And I like to think of the variable as the question itself. The question is, what color is your hair? That's the variable. And then my answer is my outcome or my data, right? And so researchers ask people questions. They ask questions about their characteristics, ask questions about the variables. And there are different types of data, different types of variables, different ways of collecting data, different ways of summarizing data, different ways of analyzing data, right? But first, we got to get a handle on what data is. It's the information we gather about people. And another vocab term we have to know is a concept called a population. Now, a population is a word that you might think you already know. And I think you're going to run across that a lot in this class. There are going to be words and terminology that I use in a very technical, specific way. And you're going to think, well, I know what a population is. I've heard that word before. But you need to learn it in this context. You have to learn about what the word population means in this class and leave sort of your everyday understanding of that word at the door, right? So in the science of data analysis, in statistics, a population is all the people a research question is trying to make a decision about. So let's come up with a different research question and see if we can wrap our head around who the populations are when we ask this particular research question. So our research question is, do Democrats vote in greater numbers relative to Republicans? And within that research question, we're asking a really broad question about a really large group of people, really about two large groups of people. We're asking a question about the variable, first and foremost, Democrats versus Republicans, right? Are you a Democrat or a Republican? I guess if you don't fall into either of those camps, you're not in my population of interest. And I'm curious about voting behavior. Do you vote or not? There's another variable. But the population here is Democrats, all of them, all the Democrats in the United States, and Republicans, all of them, all of the Republicans in the United States. That's who the two populations are when I ask this question. What you say to me, Dr. Jenny, Dr. Moses, you can't gather information from all the Democrats and all the Republicans. They're not going to answer your question. They're not all going to answer your questions. Maybe some of them will, but certainly not all of them. And you're right. But that doesn't change the fact that all research questions, all of them, are always about an entire population of people that you're trying to make a decision about. So when I ask the question, do Democrats vote in greater numbers relative to Republicans? I'm in fact interested in all Democrats and all Republicans as populations. So what is a population? Everyone you're trying to make a decision about or draw a conclusion about when you ask a research question. And as a researcher, you are the lord of your lab. You get to decide who you want to ask a question about. And so it becomes your population of interest, the population you are interested in. So let's go through a couple other examples and see if we can identify our populations of interest. And sometimes it's fairly easy, and sometimes it's a little more challenging. But a researcher's first job is to identify and define really well the population or populations he or she is interested in. That's your first job. Who do you want to know about? Who do you want to know about? And identify and clearly define that population. So here's a research question. Which freshmen are more enthusiastic about their school? Those at Pierce College or those at Texas A&M? Right? We have two populations here, right? We have two populations. We have Pierce College freshmen, all of them, and we have Texas A&M freshmen, all of them, right? And then of course we have and so that becomes a variable. Which school do you go to? Pierce or Texas? Then we also have the variable enthusiasm, right? And we're going to try to measure that. How much enthusiasm do you have, right? That's a fairly easy one. Or how about this one? In the U.S., is there a greater proportion of people with depression living in urban and rural areas? Well, if I imagine how I'm going to answer this question, I'm probably going to gather data about whether or not people have depression, right, in rural and urban areas. So I've got one variable, do you have depression or not? So, and I have another variable, do you live in urban or a rural area? But I'm going to have to gather information from people, not only who have depression, but those who don't as well. And I'm going to have to gather information from people in the rural areas and people in the non-rural areas. So when I think about all the people I'm going to have to look at, I'm going to have to look at people living in the urban areas of the U.S. and people living in the rural areas of the U.S. I'm not interested in people living in suburbia. I'm not going to head down to Orange County and start measuring people in, behind the orange curtain down there, because that would be a suburb area. I'm only interested in people in the urban areas, but all of them, so I can compare the people with depression to the people without. And then I'm going to go to the rural areas, and I'm going to be interested in all the people in rural areas living with depression and without. And so those become my populations of interest. So what about this one? This one is the most difficult example that I can give you. Who will win the 2018 congressional election in California's 3rd district, which includes LA? Well, who am I trying to make a decision about? Well, who I'm trying to make a decision about is a group of people who I don't know who they are yet. I'm trying to make a decision about the actual people who are going to show up to vote at some future point 2 years from now. Do I know who those people are going to be? No, I don't. So my population of interest is kind of hard to pin down right now. I don't know who those people are. And so that actually becomes the challenge of political polling. And so, political pollsters try to figure out who is going to be what's called a likely voter, right? And there's 3 questions they ask of voters. They ask, are you registered to vote? That's important. Did you vote in the last election? And do you intend to vote? And if somebody answers yes to all 3 questions, we can feel fairly confident that they're going to vote and vote the way they say they will when they call them up on the phone. But that's hard, right? It's a hard population to define. Some future group of people who are going to vote in 2018. So population is all the people you're trying to make a decision about, right? All the people you're trying to draw a conclusion about when you ask and answer a research question. So let's try to consider a different research question. Let's take this one. Do boys aged 5 to 9 in Los Angeles watch more cartoons in a year than girls aged 5 to 9 living in Los Angeles? Typically developed boys and girls. And so it's a very narrow research question. I'm only interested in these 2 very narrow populations, just typical boys aged 5 to 9 and typical girls aged 5 to 9 living in LA. I've narrowed it down to region, I've narrowed it down through age, and I've narrowed it down to only those who are typically typical. Now, if I was going to try to ask each and every single one of the 690 children, if I was going to try to ask each and every one of them about their cartoon watching habits, or ask their parents about their cartoon watching habits, that would take me years and years and years and years. I need a whole lot more money, a whole lot more research assistants, and way more clipboards, right? And if I could do that, that is called a complete enumeration or a census. That is called a complete enumeration or a census, right? And in psychology, unfortunately, we usually don't have access to all of the people, right? And in sociology and all the other social sciences and the medical sciences as well, because the statistics that we learn in here are the exact same in business, the exact same in medicine. Anytime you're gathering information about people, you're using the stats that we're going to learn in here. And so whenever you're dealing with people, you rarely have access to all of them. And so a complete census is very, very difficult, right? And so we have to do something different. We're going to have to do something different. Even though we are, for sure, trying to make a decision about whole populations, we're not going to be able to usually get information or data about the variables for entire populations. Just can't do it. So what do we do instead? Well, what we do instead is gather what is called a sample. Ooh, a sample. What is a sample? Again, a sample should not be the thing you go to Costco on the weekend and you go get the food samples. Yeah, no. Let's not leave that at the door. What is a sample in statistics class? A sample in our class is a smaller group of people that have been snatched or grabbed or drawn or selected It's a smaller group of people that you have selected from that larger population you're trying to make a decision about, right? So let's use the same research question from before. Do boys aged 5 to 9 living in LA watch more cartoons in a year than girls aged 5 to 9 living in LA? My samples might be, now we know there are 600,000 kids in that age range. I might grab a sample of 500 boys in that age range from LA, and I might grab 500 girls aged 5 to 9 living in LA. Now that is something I could do. I could get the resources and the time to gather data on 1,000 children as opposed to 600,000. It would take me way less time, and I could conceivably do it. And I'm going to use those 1,000 children to make decisions about all 633,000. And I can do that. I can use those samples to make decisions about populations as long as I get what's called a representative sample. A representative sample. Now, what does that mean? It means that sample can represent the entire population. Those 1,000 children can represent all 633,000 if we engage in good, careful sampling procedures. Now, it's outside of the purview of this class to go through all of the different mechanisms that you really should use if you want to have a really good sample. But we are going to go over the basics of what makes a really good sample. If you want to use a sample to make a decision about the population, you want that sample to look like the larger population. And if you do these three things, you have a really, really good shot of having your sample look like the population. Research has indicated what makes for excellent samples, right? We know what makes for good sampling. We know what will ensure smaller groups of people that we call samples to look really astonishingly similar to the larger groups of people that we call population. And if you don't think that you can use samples to make decisions about populations, next time you go get a blood test from the doctor and he wants to take a sample of your blood, you go ahead and tell him to take it all because you want him to take the entire population of your blood. Get it? As long as you engage in good sampling procedures, smaller samples can look like larger samples. So what are these good systematic procedures? Well, here they are. There's three things you need to do, and I have them in order of importance here, right? The first one is the most important. You got to at least do that, right? Then comes the second one, and then if the other two are there, then the third one is certainly nice to have. The first is actually sample from the population you care about. You're like, well, yeah. Except it's easy to forget to do this. It's also very difficult sometimes to define your population well. And if you don't define your population really well, if you don't sit down and think to yourself, who am I trying to make a decision about before you go out there and collect some data, you are not going to have a good sample. So let me give you an example. So let's say I'm trying to figure out about the overall health of U.S. football players, right? And I'm like, I'm just curious if football players are just a healthy group of athletes. And so I decide to go and to the gym here I go to the gym here at Pierce because I know that the athletes here at Pierce use the gym, and I start gathering health information from everyone at the gym. Is that a problem? Well, yeah, because the people in the gym aren't just football players. There's basketball players and volleyball players and dancers and runners and also just people using the gym, right? So I haven't selected from my population. The first thing you have to do is select from the population you care about. It's like the bare minimum, right? If you can't do that, you're never going to have a good sample. Now, so if you've done that, if you've at least made sure to sample football players, let's use this as a working example. The second thing you can do to ensure that your sample is going to represent your population well is do what's called random selection. Randomly sample or randomly select. And it's right there in the terminology. You're going to be selecting some people from your population, right? You're going to be in my sample, you're going to be in my sample, and you're going to be in my sample, but you need to do so randomly. You have to randomly sample them, randomly select them, right? And then you're going to have a much better chance of getting a sample that looks like your population. So what does it mean to randomly sample? Well, if you imagine, imagine I took all the names of all of the football players in the United States and put them in a big bucket and swirled the bucket around and then grabbed names at random. Then every single person in the population is going to have an equal opportunity, an equal probability, an equal chance of ending up in my sample. And so whatever that sort of the health is like in the larger population, when I grab my smaller sample, I'm going to have a mishmash of everybody, a mishmash of the high health people, the low health people. It's going to be a complete random assortment from the larger population, and I'm going to maximize the likelihood that my smaller group, my sample, is going to look like my population. Now, so here's a way that you can get a non-random sample. Let's say I'm interested in the health index of football players again. And instead of randomly selecting from the population, I go down to Inglewood and to our brand new football team there, and I grab the health scores of just that football team. Now, it's not a terrible thing to do, right? Because they are football players. I've at least checked off the box that they're actually football players who I'm interested in. But it's not going to be as good a sample as if I had randomly sampled football players. Third thing, if you have sampled from the population you care about, if you have randomly selected from the population you care about, then bigger samples are better than smaller samples. Now, if you're interested in, and so that means if you have a random selection of 50 football players and a random selection of 1,000 football players, the 1,000 football players are going to be better than the 50. However, remember, these three things, 1, 2, 3, 1, 2, 3, are in order of importance. So let's say I have 50 non-randomly selected athletes. Well, no, let's do 1,000. I have 1,000 non-randomly selected athletes, 50 randomly selected football players, and I'm trying to make a decision about football players. You got to go with the 50 randomly selected football players, right? The same thing. I have 1,000 non-randomly selected football players, 50 randomly selected football players. You're still going to go with the 50 because random selection is always better than non-random selection, and actually sampling from who you care about is always better than not. I hope that makes sense. If you have any questions, please post in the Q&A forum. But we're not done yet. Moving on. So to summarize, a good sample, an excellent sample that's going to be sure to look like your larger population is going to have been randomly selected from a well-defined population, and it's going to be a big sample, right? Which means you're going to have to clearly define your population. Who is it you're trying to make a decision about? Define it. Actually sample some of those people. If you can, make it a random selection. If you can. Again, if you can't make it a random selection, it doesn't mean you have a terrible sample, as long as you're actually sampling from the people that you care about. But if you can, make it a random selection. And then if you can do those two things, actually sample from the people you care about, actually make it a random sample, then bigger samples are better than smaller samples. So now, new concept. Here is the idea. So let's dive into to statistics and where that word comes from, right? This class is called Statistics 1. And where does that word statistic come from? Well, I'm about to tell you. When we talk about parameters, when we talk about populations, we're talking about a large group of people that we're trying to make a decision about when you ask a research question. For example, I want to know the height of American women, the average height of American women. Well, that population, when I ask that research question, that has some reality out there. There is some average height for American women. It's a numerical value, right? It happens to be 64 inches. The average height for American women is in fact 64 inches. And so the average height is in fact 64 inches. You call it 5'4". And so that 64 inches is what is called a population parameter. 64 inches is a parameter of the population American women. It's that characteristic of their height. Their average height is 64 inches. And we call that a population parameter. It's a characteristic of a population, and specifically a numerical characteristic. Like the average height is 6'4". The average number of children is 2. All of those are examples of population parameters. This is different than a statistic. A statistic is a number that you calculate for a sample. Now we know we're going to use our samples to make decisions about populations. We know we're going to do that, right? We're going to use our samples to make decisions about populations. And so essentially, we're going to use our statistics, our sample statistics, to make decisions about our population parameters. And so let me give you an example. So let's say I'm able to grab 100 women from the United States, and that is my sample. And I calculate their height, and I calculate it as 64.5 inches. Well, that's a sample statistic. That average for my sample, remember what an average is? You've probably calculated it a bunch of times. You add up a bunch of numbers and you divide by those same number of numbers, right? Like if I have 3 women, the first one has 1 child, the second one has 2 children, and the third one has 3 children. I take 1 plus 2 plus 3, I get 6, divide by 3 to end up with 2. The average number of children for these 3 women is 2, right? The average. Now, if I get 100 women and I calculate their average height, their statistic, right? Because it's only 100 women, it's only a small sample. If I get their average height of let's say 64.5 inches, that's a sample statistic. And I'm going to look at that sample statistic and I'm going to go, I bet the population parameter for height is also pretty close to 64.5 inches. Now I happen to know that the population average is 64, but let's say I didn't. I would use my sample average to make decisions about my population average. And so my sample average is the statistic, and my population average of 64 is the parameter. Make sense? Good. Well, at least I hope so. There's no like back and forth. It's just a camera. Oh, well. So the next thing I want to talk about is the symbols that we use to represent parameters and statistics, because this class is all about symbols. It's all about using symbols to represent different numbers. Now, most of you are probably familiar with the symbol pi from math. It's 3.14116 on and on and on and on and on forever, right? Pi. Pi is a symbol that represents a specific number. It represents 3.1416. This class uses a lot of symbols to represent numbers, specific numbers. For example, a population average is always symbolized as the Greek letter mu. This is the Greek letter mu right here that I am circling, circling, circling. This is the Greek letter mu. This is also the Greek letter mu in a slightly different font. It kind of sort of looks to me like a really weird M or like a really weird U, but it's not. It's the lowercase Greek letter mu, right? The Greeks have their whole different alphabets. It doesn't look like our alphabet in English, right? Or, any of the, English or Spanish or, French. We all use the same alphabet, but the Greeks don't, right? So this is the Greek letter mu. And it's a symbol And pi is actually a Greek letter as well. It is the symbol that always represents the population average, always. Now, different populations have different averages. The same population has different averages on different things, right? Like the population average for height for women is 64 inches. The population average for weight isn't 64. It's, I don't know, 140 pounds maybe, but we would still symbolize that as mu, except it's just the mu for a different variable, right? A different characteristic. That's the idea. But a population average is always symbolized as mu, as that Greek letter. And in fact, all population parameters are always symbolized as Greek letters. Now, this here is called sigma. It's the Greek letter sigma, lowercase Greek letter sigma, not to be confused with that sigma that we learned about yesterday, which is a mathematical operator that means add up a bunch of things. I guess not yesterday, but before, the last lecture. This is the lowercase Greek letter sigma, and it represents something called the population standard deviation. It's not important that you know what kind of number the standard deviation is. All that's important right now is that you know that this does represent a number, just as mu represents the average. This represents another number that you could theoretically calculate for an entire population. This one here is the Greek letter rho. It's not a P, it's the Greek letter rho. And it's the correlation for a population for two different variables. You smush those two variables together and you can get a correlation. And so Greek letters, without exception, population parameters are represented with Greek letters, with funky looking letters. Statistics, on the other hand, are always represented with regular letters. They're actually called Roman letters. You may not have known that, but our alphabet and the French alphabet and the Spanish alphabet, all of those letters are what are called Roman letters. Think of them as regular letters. And so let's use the average height example again. If I grab 50 women and I calculate the average height of those 50 women, that is going to be a statistic, and I'm going to symbolize that with this symbol here. This symbol is called X bar. So named because it's an X with a bar on top. That's really what it's called. It's just the symbol that represents an average for a sample on a particular variable. Like there might be X bar equals 64 or 64 and a half or whatever the average height is for that sample. This is the regular letter S. It stands for the standard deviation of a sample. This is the regular letter R. It stands for the correlation for a sample. And again, it's not important you know what the standard deviation or the correlation are now, but recognize that regular Roman letters, are used without exception to represent statistics, which are numbers that you calculate for samples. And you also notice these little like baby letters down here. These are called subscripts, and they're what are called for your information. Now, and what we essentially do in statistics is we label our variables with letters. We label them with letters. So let's say I'm exploring height. I would label height X. Let's say I'm also exploring weight. I might label weight Y. And so then this would be the standard deviation for height, which I've labeled X, and I know that because it's got a little X here. This would be the correlation between X and Y. So the correlation between height and weight, and I know that because I labeled height X and weight Y. These little subscripts are always just for your information. They're letting you know this is a standard deviation because this is the symbol S. It stands for a sample standard deviation, but it's the standard deviation for the X variable. So in this case, height. Here is the correlation for the X variable and the Y variable, height and weight. So subscripts are always just for your information. And sometimes they're letters, sometimes they're numbers, and really you can make them anything you want. They're just keeping track of, oh, this is an average. What is it an average for? Oh, it's an average for the X variable. It's the average for the men. They're called subscripts, and they're for your information. And you're free to make them whatever you wish. They're usually X, Y, or a number. So, to sum up this sort of big topic, We are going to collect small group. We're not actually going to do any data collection in here. But researchers gather information, gather data from small groups of people that we call samples. They then calculate some numbers that they call statistics, and then they use those statistics to make decisions about populations and what those population parameters might be. So I'm going to grab a sample of 50 women, calculate the average statistic for height for those 50 women. Then I'm going to decide how the population of women everywhere, what their population parameter for height might actually be, right? And why do we have to do this? Well, it's because we don't have access to populations. We just don't. As social scientists, we have to use samples to make decisions about populations, and that's actually why we need statistics at all. If we had access to every single person and all the information about every single person, we would never ever have to calculate statistics, right? The whole purpose of this class is to learn the tools that allow us to use small groups of people and their statistics to make decisions about large groups of people and their parameters. We use sample statistics to make decisions about population parameters. So, quiz time. Well, not a real quiz, but just a way to test yourself. Here's a research question. I want to know the average height of women at the university at CSUN, so I collect 50 women from around CSUN and measure their heights. What's the population? All the women at CSUN, right? All of them. All those women at CSUN. Who's your sample? The actual 50 women you coerced to come and talk to you, and where you whipped out your tape measure and measured their heights. So, moving on. Other vocab terms that you need to make sure you know is the concept of a variable. It can be a little bit of a confusing concept. And so let me try to break it down for you. A variable is a way that people can be different. It's a question you can ask about somebody. The variable is how they can be different. For example, hair color, right? Hair color is a variable. The fact that I have light brown hair or reddish hair is my outcome. Having blonde hair is not a variable. Hair color is a variable because that's how people can be different. To say I have blonde hair, that is not a variable. That's my answer to the question. I have blonde hair. I have light brown hair. I have red hair. I have black hair, or whatever people say, right? Or if I ask you, how many cups of coffee did you drink today? Caffeine intake would be a variable. Now, when I tell you I had 2 cups of coffee today, 2 cups of coffee is not a variable. That is an outcome. That is my answer to the question. The variable is the question. The answer is the data. So be able to distinguish between those two ideas, right? And variables and data come in different varieties. And before I launch into this discussion, because we're going to learn about the difference between qualitative and quantitative data, I have to point out to you that your book has this really interesting discussion about the difference between qualitative and quantitative research. And it's an interesting discussion, but it's separate from what I'm about to share with you. It's one of the unfortunate parts of statistics that oftentimes the same word, the exact same word, can be used in 2 very different ways depending on the subtopic within statistics. And unfortunately, there is no book out there that teaches exactly like I do. There's just not a book out there that does that. The book I've selected for you, we have, maybe about 60% overlap, right? And that's pretty good. And I've selected your book because it is the least bad. There really aren't any good stat books out there, unfortunately. I've read about a dozen of them. And the one that I've assigned to you gets some things just a little sloppy about some things, to be quite frank. And this is one of the areas where they're putting the emphasis on the wrong thing. Now, the difference between qualitative and quantitative research is really a topic best sort of tackled in a research methods class. right? And research methodologists talk about qualitative versus quantitative research, and all that's very interesting, and you'll read about it in your book. However, that is entirely, completely, and utterly different from the difference between qualitative and quantitative data. Same words, very different discussion. So put the book's discussion of this sort of on the back burner of your mind, because qualitative versus quantitative data is just way more important for you to understand in our class than how your book talks about those terms. I'm not going to say your book is wrong. It's really a topic for a different class. It's a topic for a research methods class. It's one of the unfortunate things that sometimes you have these words get used in more than one way. So for our discussion, variables and data, variables are the questions, data is the answer, fall into two different types, two different broad types of information. Sometimes you have qualitative or categorical information about people. And this is the kind of variable or the kind of question that will give you data that is a word, that is a quality or a category that somebody is falling into. For example, and so I like to think of this as group-based variables that are going to give you like a group-based data. So for example, in research, gender and biological sex are almost always asked in this fashion, where we say, check one of these boxes. Are you male, female, or other, right? Are you a man or a woman or other, right? So that is an example of a group-based variable because we're putting people into different categories or groups. And so if you think about the variable, gender, or what is your gender, someone is going to give me an answer that is a word. I'm a man. I'm a woman. I'm intersex. I decline to state. I don't like your question. Either way, it's going to be a word, right? Or if I ask you, are you a Kings or a Ducks fan? Because you cannot be both. Are you a Kings or a Ducks fan, right? The answer to my question, the variable, is which are you? Kings or Ducks? That's the variable. That's the characteristic on which people can be different. And someone says, I'm a Ducks fan, or another person says, I'm a Kings fan. The answer is a word. The data itself is a quality about them. The quality of being a Ducks fan, the quality of being a Kings fan. They're in a particular category. And so it is a categorical or qualitative variable. The data itself is qualitative. Quantitative variables, on the other hand, generate quantitative data. And this is what we call a continuum or a range-based variable, where people can be different along a continuum from high to low. So you might ask, how much aggression do a group of children have? Where some children have like an aggression index of 57 on a scale of 0 to 60. Another child is going to have a score of 32 on an index of 0 to 60. Another child is going to have a score of 5 on a scale of 0 to 60, right? There's a continuum there where people are different in terms of amount, in terms of quantity. One child has higher aggression than another child does. Or caffeine intake. How much coffee did you have today? 1 cup, 2 cups, 3 cups, where there's going to be a dimension of how much coffee from high to low. And so anytime you think about a variable where you're going to ask someone the question and the answer to the question that they either give you or that you generate for them is going to be a number, you have a 57 on the aggression index. You have 3 on the variable, how much coffee do you drink? Right? Because you have 3 cups of coffee. Then you have a quantitative variable. Now, again, this is totally different than how your book talks about these words. That's because they're talking about a research methods topic, and I'm talking about a statistics topic. I don't know why they decided to launch into research methodology in a statistics book, but whatever. It's one of the many slappy things about your book. And so don't get confused. It's about the answer to the question, right? So let's think about gender and how gender is a qualitative variable, right? Because I don't want you to take it to mean anytime you have numbers, you always have quantitative data, because that's just wrong. Anytime you have a number, you have quantitative data. No, that's wrong. Because it's about the variable itself. Is the data a word? Qualitative. Is the data a number? Quantitative. Because let's say I'm keeping track of in this class, there are 20 women and 15 men and 2 people who are either none of the above or intersexed or declined to state, right? The one person said woman, the next person said man, the next person said declined to state, and the next person said woman, and the next person said woman. And I keep track of the fact that there are 20 women and 15 men and 2 people who declined to state. That is still qualitative data because the information that came at me was a word. This person is a woman. This person is intersexed. Qualitative data, right? So it's about the answer to the question. If it's a group-based variable, if you're putting people into groups, men, women, other, qualitative. If you're looking along a dimension from low to high, from faster to slower, from smaller to bigger, whatever, if there's a range where you would put people in order at least, you definitely have a quantitative variable. And it is the most important way to classify data in our statistics class. And it's the way of classifying data that gets the least amount of coverage in every textbook I've ever read. Because whether or not you have qualitative data or quantitative data dictates the kind of data analysis you can do. Literally, the equations that you can use on data differ depending on whether or not you're shoving people into groups, kings or ducks, or you're looking along a dimension. How much caffeine do you drink? If you're asking people to choose, are you this or are you that, this, that, or the other thing, are you a Kings fan, a Ducks fan, a Flyers fan, right? No matter how many categories you have, if you're shoving people into distinct categories, there's a different kind of analysis you can do on that than if you're gathering information about a range of responses, like high to low, faster to slower. How fast you can run a mile is a quantitative variable. And there's a different set of equations you can use on that kind of data. So this is the single most important way to think about your data. Do I have a group-based variable? Or do I have a dimension, fast, slow, high, low variable? It's the single most important way to think about data. So let's look at some research question and make sure we can identify the variables and think about whether or not they are qualitative or quantitative, right? Are they group-based variable or are they a high to low variable? So do men and women differ in extroversion? Well, man versus woman, not very inclusive research question. I don't even have an other category on there for people to choose. What is wrong with me? Do men and women differ in extroversion? Well, men versus women, that is a qualitative, categorical, group-based variable. Extroversion is probably measured quantitatively, or I'm probably going to give people some survey that asks them a bunch of questions. On a scale of 1 to 7, how talkative are you? On a scale of 1 to 7, how outgoing are you? On a scale of 1 to 7, how extroverted are you? Where I'm going to get some people who are very extroverted, some people who are not as extroverted, some people are even less extroverted, and some people who are not extroverted at all. So I'm probably going to have a dimension base for extroversion. Is depression more of an urban or rural problem? Well, depression is a variable, and I'm probably going to measure it from high to low, where I'm going to give people like a survey about their depression that asks them a bunch of different questions where they circle how worthless do you feel from 1 to 7? How guilty do you feel from 1 to 7? How often are you crying every day from 1 to 7? Where they're giving me answers about the extent of their depression, high to low. So we have a quantitative variable. Urban versus rural, of course, is going to be a qualitative variable. Do you live in an urban area or a rural area? Does TV watching relate to childhood aggression? Well, TV watching is probably not going to be, do you watch TV or not? It's probably going to be, how much TV do you watch? 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours, 7 hours, right? And so we're going to have a quantitative variable of TV watching. Childhood aggression is also probably also quantitative, because I'm probably not going to say, are you a non-aggressive child, because there's no such thing, versus a very aggressive child. I'm not going to have just 2 camps or 3 camps of aggression. I'm probably going to measure this specific amount of aggression that children have. And I'm probably going to give them a number for how aggressive they are, with 5, 6, 7, 8, where, 10, 20, 40. 40 is going to be more aggression than 5 is, right? Quantitative variable. Or how about, does marital conflict make divorce more likely? Well, marital conflict, again, is probably going to be quantitative. More marital conflict versus less marital conflict, right? 1 fight, 2 fights, 3 fights, 4 fights, 5 fights, where higher numbers mean more of it. Versus, but divorce is a qualitative variable, categorical variable, where I'm going to say, are you divorced or not? And I'm going to keep track of how many people are divorced. 50 people are divorced, 100 people are not divorced. It's still a qualitative variable, because when I asked them the variable question, are you divorced? They gave me their data. No, I'm not. See how it's a word? Qualitative data. You cannot be a little bit divorced. I promise. You either are or you are not. You're putting people into categories. Qualitative, categorical data. So, next topic. After I just sort of, criticized the book for covering research methodology, I'm about to cover a little teeny itty bitty bit of research methodology. It's not central to our course. It's not central to things we're going to do from here on out. But I do want to give you just a little bit of background about research methodology. And really, I just want to teach you the difference between true experiments in research versus what's called observational data. In a true experiment, a researcher manipulates things. They actually mess with people. They manipulate something called the independent variable. And I like to use the working example of a drug study, right? Let's use marijuana as an example. It's more and more states are legalizing marijuana. It's on the ballot here in California this year. And as a medical researcher, you might be very interested in like the long-term effects of marijuana. So you might decide that you're going to do a true experiment to see what the long-term effects of marijuana are on, developing brains. And so you recruit 100 people, and you're going to then manipulate whether or not they smoke marijuana. You're going to create a qualitative group-based variable, an independent variable that you independently, as your lord of the lab, manipulate, right? You manipulate this independent variable where you give half the people marijuana and say, smoke this whether you like it or not. And you give the other half of the people no marijuana. You say no marijuana for you, whether you like it or not. And that becomes your independent group-based variable. Then later on, you measure, let's say, their brain activation patterns, or you measure their motivation. That then becomes your dependent variable, and it's usually quantitative. You measure their amount of motivation. You measure their amount of brain activation in certain areas of the brain. And when you do that, when you as the researcher get in there and mess and manipulate the independent variable to then watch to see what your group-based independent variable, and then watch to see what happens to your quantitative dependent variable, you have got yourself a true experiment, and you can talk about cause and effect. You can say, if you find differences between your groups, you can say, smoking marijuana causes changes in people's brains or causes changes in motivation, right? That is called a true experiment because you're actually manipulating things. All other kind of research is called observational or correlational in nature. Observational and correlational are a little bit different if you take a research methodology class, but for our purposes in this class, you can really treat them as the same. You can treat them as not a true experiment, where you're just sort of observing the world as it is. You're not manipulating things. You're not messing with people. You're just sort of watching the world as it happens, even if you're doing so in a systematic manner. And so then we talk about predictors and criterion, right? Because I might want to, let's say I don't want to have to actually like force people to smoke marijuana. Well, not force, but I don't want to manipulate marijuana use. I don't want to say you 50 people do that and you 50 people do that. I don't want to have to do that. I don't want to do a true experiment. I could just ask people, how much marijuana do you smoke? I can then measure their brain activity. And then instead of calling marijuana use the independent variable, because I didn't independently manipulate it, I'm just going to call it a predictor. And then brain activation patterns or motivation don't become a dependent variable because I didn't manipulate anything. Rather, they become criterion variables. And so the terminology changes a little bit. And what you need to know for the purposes of this class is you can only say anything about cause and effect, A caused B, X caused Y, smoking marijuana causes things to happen in the brain. You can only do that if you do a true experiment where the researcher manipulates things actively. If you're simply observing or measuring things as they actually are in the world, you're doing what's called an observational or a correlational study, and you can't make statements about cause and effect. You can't say marijuana causes anything. You can just say they seem to be related in some fashion. And we'll return to this a little bit more at the very end of the semester. But again, it's not central to our discussion right now. It's just a little background knowledge about research methodology. All right, but if you are going to do a true experiment, you do need to do something called random assignment. Now, this is different than random selection. Remember how random selection is always super important? It's how you make sure your samples look like your populations. Well, there's another phrase called random assignment, and it's only relevant if you're doing a true experiment. And you can do statistics on any kind of study that you want. You can do statistics on observational data. You can do statistics with a true experiment, right? That statistics doesn't care how you got your data, right? It doesn't care what kind of research you're doing. However, when you do random selection, that's how you get your sample. In all kinds of research, you should have random selection, right? And in all kinds of research, you're going to do statistics. And in all kinds of research, you're going to have variables. But random assignment is only relevant if you have what's called the true experiment, right? And that's really what makes a true experiment. It's essentially how you decide which group your people go into when you do that true experiment, where you're manipulating a group-based independent variable. It's essentially you just have to flip a coin. You have to randomly do it. You have to say, okay, this person from my sample, you go into the marijuana group. Flip a coin. This person in my sample group, you go into the non-marijuana group. No marijuana for you. Flip a coin. Oh, you also go in the no marijuana group. Flip a coin. Oh, you go in the marijuana group. You're randomly assigning people to what are called experimental conditions. There's usually a control group that doesn't get the drug or doesn't get the marijuana or doesn't do something, and then there's another group that does actually experience something. It's called the experimental group, and you have to randomly assign people in order for it to be a true experiment, right? And it's random assignment that is required in order for a true experiment to be meaningful, in order for a person to make good statements about cause and effect. But don't get confused. Random selection is always important. It's always good. No matter what kind of study you're doing, you always want random selection. It's how you get your people. Random selection is what is needed in order for your sample to look like your population, no matter what kind of study you're doing. True experiment, correlation, who cares, right? Random selection is always required if you really want your samples to look like populations. Random assignment is only relevant if you're doing a true experiment, and true experiments are where you're randomly assigning people into different groups that are going to experience different things so that you can see the effect of your manipulations. Like, I'm going to manipulate whether or not people smoke marijuana. It's the independent variable to see what effect that has on the dependent variable. Let's call it motivation, right? Where the independent variable is usually group-based and the dependent variable is usually some dimension-based variable like motivation, high to low, right? Random selection is how you get your people. Random assignment is what you do with them once you have them, but only if you're doing a true experiment. So just a tiny little bit of research methodology. And here are some examples of observational research methodologies. Here, and they're just words. They're just phrases for you to know, to file in the back of your brain. There's something called naturalistic observation, controlled observation, any kind of survey you've ever taken, standardized testing like the SAT, observational research. Any type of correlational, you may have heard that word before, is observational research. So, to review, the most important way to classify data is the one that we've already gone over. Quantitative versus qualitative data. Quantitative versus categorical data. Quantitative is where you're measuring an amount of something, more to less, where the question, the variable, is going to generate data about the person that is a number. The person is going to have more or less, right, than somebody else, right? So like the amount of aggression or the number of books somebody has in their library at home. I have hundreds of books. Other people have like 6, right? It's a quantitative variable because I have more than a lot of people, but I only have, I only have 1 car. Some people have a lot more cars than that. Or I only own 1 spatula. Some people own lots of spatulas. I own 2 pans. Some people own way more pans than I do, right? The amount of depression that a person might have, more versus less. The number of children people might have, more versus less. All of these are quantitative variables versus categorical variables, qualitative variables, right? Where it's either all or nothing. You either are in the category or you aren't. You're either in this category or you're not, right? For example, independent variables from experiments are usually categorical or qualitative. You're either getting marijuana or you aren't. Someone's favorite color, right? The variable is favorite color, and when they answer the question, they're going to tell you red, green, blue. I might keep track of the fact that there are 10 people who like blue and 5 people who like red. It's still a qualitative categorical variable. Gender is usually measured as a group-based this or that, all or nothing category. Ethnicity is usually measured in this way. If you've ever taken like some demographic survey, they say, okay, pick one, right? And you've got, white or Caucasian, black or African American, Asian American or Pacific Islander, Latino or Hispanic, and then you have the other box. And they're like, but I want to choose more than one of these, many people feel, and they don't let you, right? It's lame, but that's how we usually measure it. We usually measure ethnicity as this or that. Can't be in the middle. Got to choose this or that. Qualitative categorical variables. The most important way of classifying data, classifying variables, is this way. However, there are 2 other ways of classifying data, and that are not as important, but you need to know them because a good, well-rounded statistical education will have exposed you to these ideas as well. What we went over on this other slide, most important way. It's the way I want you to know from your spine. I want you to know it so well, it's like a reflex. I want you to be able to fully understand the difference between qualitative and quantitative data. But a second way is something called discrete, continuous, or semi-continuous. And think of this as just a completely separate question to ask yourself about data. You can first ask, is it qualitative or quantitative? And this is just a second question you can ask about it. Is it discrete, continuous, or semi-continuous, right? Discrete data means you can't be in the middle. It can still be a dimension-based quantitative variable, but you can't cut the outcomes in half. So things like this are going to be the number of children that you have, right? People don't have 2.5 children. That is not a thing. It's a quantitative variable. It's absolutely a quantitative variable. 0 children is fewer children than 10 children, right? It's a dimension-based variable, but you can't have 2.5 kids. You can't cut the outcomes in half. So it is a discrete variable. Discrete means separate. The outcomes are separate and finite. There's a limited number of possible outcomes because you can't chop them in half, right? The number of kids a group of people might have may range from 0 to 10. And you have 0 or 1 or 2 or 3 or 4 or 5. You don't have 4.5 kids. That's not a thing, right? Or the number of majors at a university. Some universities have more majors or some universities have way more majors than others do, right? But you're not going to have like half a major. That's not a thing. Or the number of books in a library, right? It's certainly quantitative, more books versus less books, but you don't have half a book, right? So some quantitative variables are discrete, and all qualitative variables are discrete. gender, ethnicity, right? They're just by their very nature discrete because it can't be in the middle of two categories. You can't like chop it in half. This is different than a continuous variable. Now only quantitative variables can be continuous, although not all are. But a continuous variable is one that you can sort of cut in half. So these are going to be things like physical attributes, like how fast can you run a mile? Well, you can run a mile in 4 minutes, you can run a mile in 5 minutes, or like me, you can run a mile in 20 minutes with many breaks, right? But you can run 4.5 minutes. You can run it in 5.5 minutes. You can run it in 4 minutes and 4.25 minutes. You can run it in 4.1 minutes. You can run it in 5.16735. You can keep sort of getting finer and finer and finer and finer and finer and finer and finer measurement all throughout it, right? So there's theoretically an infinite number of possible mile times ranging from 4 minutes, the fastest anyone's ever done it, all the way to my mile time, which is like 20 minutes, right? You have an infinite number of possible mile times in between those two endpoints, right? It's not like the number of kids you have where you jump from 0 to 1 kid. There's no half kids. That's not a thing, right? But you can jump from 4 minutes to 5 minutes, but then there's everything in the middle. So it's a continuous variable, continuous. And then there's this fudge factor in psychology and the other social sciences. It's called semi-continuous. And semi-continuous is not actually a real thing in like statistical theory. Like in real statistics, semi-continuous, not a thing. But in psychology, we have this phrase because most of the things that social scientists, anthropologists, people who do business research, people who study people's psychological characteristics, we're really interested in these psychological variables like aggression and things that are sort of hard to pinpoint in a physical way. And they're theoretically continuous, right? Like let's talk about aggression. Let's say I give somebody an aggression score of 6 and I give somebody else an aggression score of 7. Like theoretically, I bet there are people that fall in between those two individuals, but I haven't measured it in that way. I've actually measured it in a discrete way. I don't give people a 6.5 on this. They are either a 6 or a 7, but theoretically it's continuous, but I've only measured it discretely. And so we call it a semi-continuous variable, which is just sort of a BS fudge factor, right? And so this is a less useful distinction, but I do want you to memorize it and know it because you, as a well-rounded statistical, any well-rounded student of statistics should be familiar with these terms. We're just not going to use them a whole lot, right? We're going to be using that qualitative versus quantitative distinction a whole lot. We're going to use this less often. And last, and definitely least, is the worst way to classify data, the most terrible way to classify data, the way of classifying data that does you no good unless you're an advanced statistics student in like some graduate program in quantitative psychology who enjoys debating the most esoteric, mysterious nature of variables. But it's the one that's covered the most in almost every intro to stat book. So you need to know it as a person who's competent in statistics. And it is essentially called Stevens' 1946 Scales of Measurement. And it's just a different way of classifying data. It's yet a third question you can ask about your variables, and thus a third thing you can ask about your data. And just like you can classify a variable and thus classify data, remember the variable is the question, the data is the answer to the question. Just like you can classify variables and data as qualitative or quantitative, and you can classify them as discrete or continuous, right? It's a separate question you can ask. You can also classify data as nominal, ordinal, interval, or ratio. Essentially different variables and thus different data fall into one of these 4 camps. And this sort of classification scheme is not magical. It was a gentleman named Stevens, that's his last name. He wrote this very short paper in 1946. where he sort of looked around at psychology as it existed then and said, hey, look, people are like measuring things about people. I'm going to decide how they're measuring people, and I'm going to classify different kinds of data, right? It's not like written in stone or anything. It's just his way of classifying things that people have found useful over the years. I don't find it particularly useful. For me, I care about it. Is it qualitative or quantitative? That's what I care about. And there are many people who agree with me. But you should be, and you will absolutely be tested on the nominal, ordinal, interval, or ratio distinction. We'll learn it, we'll get tested on it, and then we'll never return to it again all semester. So, what is it? Nominal. Nominal is sort of just another word for qualitative, categorical. That one we already learned? Yep. Nominal is just another word for that. So gender, ethnicity, are you married or not? What is your favorite color? What kind of car do you drive? And nominal actually means word. It actually means name. And so just like categorical data, the answer to the question is going to be a word. Nominal data is where you've gathered information about people and it's a category or a word, right? And so then there's the last three. Ordinal, interval, and ratio. And essentially what Stevens did is he goes, well, there's nominal data, categorical data. He called it nominal because life wasn't complicated enough, right? He called categorical data, qualitative data, nominal. But then he said, there's like 3 different ways to be quantitative. That's what he said to himself. There's like 3 different ways to be quantitative. And the first way to be quantitative is to just put people in order. Don't measure them specifically. Don't ask them how many cups of coffee they had. Just figure out if they had a lot. And put the a lot people over here. And then put the no people over here and put the little more people over here. And right, just put people in order. Don't measure specifically how much coffee they've had. Just put people in order from the most to the least. And then give them a number based on their rank. So this person on the far end could have had 16 Red Bulls today, but there's only 10 people in the group because it doesn't matter if they had 16 Red Bulls. I don't care if they had 16 Red Bulls. I'm just going to give you the number 10 because you had the most. And the person over here, the other far end, had no caffeine today. But since they had the least, I'm going to give you a 1. You're not measuring a specific amount of anything if you're simply putting people in order. And the kind of variables that are ordinal are like the places in a race, right? The Olympics just got over. The gold, silver, and bronze medal categories are example of ordinal data, right? It's still quantitative. The person with the gold medal has more success than the person with the bronze medal, right? You can rank them 1, 2, and 3, but you didn't measure a specific amount of success, right? You didn't measure anything specifically. It's not as if the gold place person has the exact same difference between the silver place person as the silver place person has the difference between the bronze person. You're just rank ordering people. And that is called ordinal because you're simply putting people in order, and that's it. Not measuring a specific amount of anything. Interval, on the other hand, you are measuring a specific amount of things. You are keeping track of exactly how much stuff people have. So it's a little more quantitative than ordinal. It's like more quantitative, where you're keeping track of the specific amount of something, and you want to keep track of it specifically because when you give someone a number, you want to make sure the differences between the numbers you're giving people are the same no matter where you are on the scale, right? So if I give this person a 7 depression score, and I give this other person an 8 depression score, and I give this other person a 9 depression score, I want to try to make it so the intervals between those scale points from 7 to 8, from 8 to 9, from 9 to 10, those are what are called intervals, the interval between the numbers. I want to make sure those intervals are the same. But I don't have to make sure that 0 means none of it, right? So, and what I mean by not a true meaningful 0 point is in an interval measurement, 0 doesn't have to mean none of the variable that you're measuring. So a good example of interval measurement is temperature. For example, temperature, let's say Fahrenheit, right? You've got 0 degrees, 1 degree, 2 degrees, 3 degrees, 4 degrees, 5 degrees, 7, all the way to 100 degrees, and all the way to 120 degrees, right? And between every single degree point, there's been the exact same amount of change, no matter where you look on the scale. And that's true with Celsius as well. The difference between 1 degree, 2 degrees, 3 degrees, 4 degrees, 45 degrees, 46 degrees, as you move up and down the Celsius scale, the change in temperature is the same as you move up each degree. But in both of those temperature scales, 0 doesn't mean no temperature. It doesn't mean a lack of something, right? It's not like when you get to 0 degrees Fahrenheit, something stops or there isn't something. It's not none of it. In fact, the 0 point on the Fahrenheit scale is at a very different place than the 0 point on the Celsius scale, even though they're both measuring temperature. So the 0 points are what we call arbitrary on an interval scale. And most psychological variables are interval because we want to measure a specific amount of aggression. We want to measure a specific amount of depression. We want to measure a specific amount of stuff in people's psychological realities. But if we happen to have a 0 point on our scales, it usually doesn't mean no aggression or no depression or no anxiety or no whatever. It's just sort of an arbitrary 0 point on the scale to mark where it is on the number line. Because there's one final way to be like a super quantitative variable, the most quantitative variable of all the quantitative variables. And that is to be what is called ratio measurement. Variables, and thus data, can be what is called ratio, where you have true mathematical precision in your measurement, where you have a 0 point on your measurement scale. That means none of it. You have none of whatever you are trying to measure. For example, how many cups of coffee did you have today? If you say 0, that means you had no coffee. How many children do you have? 0. I have no children. How fast is that car moving? It's not moving at all. 0. No movement, right? What is your reaction time, right? 0 would be 0 seconds. Now, whether or not anyone can actually do a reaction time of 0 makes not a bit of difference. 0 on that scale of seconds would mean no seconds. And what's nice about true mathematical ratio scales is you can start talking about twice the amount and half the amount. You can start talking in terms of ratios, right? And let's compare and contrast. So let's say, let's take temperature, which we know not to be ratio. It's only interval. If it's 90 degrees here in the valley and 45 degrees up at Big Bear, we don't have twice as much temperature as they do up here, right? In fact, if we switch to Celsius, we would no longer have twice as much, right? There wouldn't be a doubling of the degrees. Their ratios don't make sense. But if somebody else, let's say I have 2 children and somebody else has 4 children, because 0 means no kids, a person with 4 kids does in fact have twice the amount of children that I have. And it's the most quantitative, the most mathematically rigorous type of measurement is ratio. But once again, Stevens' 1947 is not a magical way of classifying data. It's really just a sort of an interesting sort of thing to think about. How quantitative is your quantitative data? And really where the debate comes in is really in psychology, where we ask the question, are our psychological variables ordinal, or are our psychological variables interval? Most of the time we assume that our variables are interval. Some people argue that psychological variables are only ordinal. And why this matters is whether or not you think it's okay to calculate an average for an ordinal variable. I think it's just fine. GPA is an ordinal variable, right? A, B, C, D, F. We give A's a 4, we give B's a 3, we give C's a 2, and we give D's a 1, and F's a 0. And then we average them. So to me, it's a really sort of advanced topic, but you should just be aware of what nominal, ordinal, and interval and ratio are. We've learned them now. You're going to be tested on them. You're going to need to learn to recognize nominal, ordinal, and interval variables. But after we're tested on them, we're going to leave them behind. Because what's much more important is, are your variables qualitative or quantitative? Are you shoving people into groups, or are you measuring people along a dimension? That is the most important way to classify data in our class, which is why I call it classifying data way number 1. And that is the one I want you to spend the most time making sure you understand. All right, thank you very much. I will see you next time, where we will talk more about measurement.